Okay, so welcome to the to a new module, module number 10 in the lecture series on VLSI testing. So, what we have dealt till now in the test series in the discussion on test were regarding combinational circuits. So, we have started with fault models, then we have seen for random test pattern generation, then we have seen fault collapsing, co-op algorithms, synthesize, propagate and justify based algorithm as D algorithm and so forth, but most of them were limited to combinational circuits. So, in the new module 10, we will mainly look about how the same things or all the technologies like stacked fault models, collapsing etc., ATPG algorithms etc., whatever we have seen for combinational circuits, how they map to sequential circuits. So, this lecture is today we learn on automatic test pattern generation for synchronous sequential circuit. That means, you should also know that sequential circuits can be synchronous as well as asynchronous, which we have learned in our basic digital days, but actually here we will be mainly dealing with synchronous sequential circuits with a single clock. I mean, to make the course a bit simple, because this course is mainly on the VLSI design, verification and test. So, we are going to have an overview of almost all the three aspects of VLSI design. So, rather than going into in depth of asynchronous circuit testing and so forth, we rather thought that we will try to give you a broad overview. So, to limit the depth of sequential circuits ATPG, we will limit our scope to single clock synchronous circuit, and most of the digital designs we do these days are basically driven by single clocks, and it is mainly sequential in nature. So, I mean, this actually covers the main part of VLSI testing for sequential circuits, and a very few limited circuits you can think of run asynchronously. So, more or less, even if you are not covering that, but that does not have too much impact on our VLSI testing study. So, basically what we will study. So, I mean, we have seen combinational circuits from the last 3 days. So, now today we will see for the sequential circuit, that is having a clock. So, what is the verification required? So, we will see what is required in the fault model. So, we will just see that the fault model is absolutely similar in case of combinational and sequential circuits, but as one or two small assumptions may be there that we will point out. So, we will see that there will be a requirement of a higher order algebra for sequential circuit, and we will see the ATPG procedure, and we will see how different is ATPG in sequential circuits compared to combinational circuit. That is what we will see. In the next lecture, maybe we will see something like a scan chain etc., so which can help you in ATPG. So, we will show that the ATPG procedure complexity in case of sequential circuit is much higher than in a combinational circuit. So, following that we will find out a design technique called scan chain, which will help you to reduce the complexity and which will help in ATPG for sequential circuit. That will be in the next 2 lectures maybe. So, I mean, so test pattern generation for we will see the scan chain, and also test pattern generation for a sequential circuit with scan chain can be generated with single ATPG algorithms, D example and all. So, this is about in details we will see slowly. In today's class what we will discuss, we will mainly see what is ATPG about different, why is ATPG different in sequential circuits, and then we will see that in the next lecture, and also we will point out that ATPG for sequential circuit is more complex than combinational circuit. So, followed by, so in next lectures we will see that how we can develop something called a scan chain, which will convert your sequential circuit to a virtual combinational circuit, and then all algorithms which developed for combinational circuits can also be applied to sequential circuits with a scan chain without any much change. So, in that way we will handle the complexity of ATPG for sequential circuits, but that will be in a later half of the lecture. So, that is why it is said that basic motivation of developing this 3 lectures or 4 lectures on sequential ATPG will be to convert, we will first study the complexity of ATPG for sequential circuit compared to combinational circuits, and then convert the sequential circuits to virtual combinational ones using scan chain, so that ATPG algorithms for combinational circuits like D algorithm etc., can be applied to sequential circuit with a variation. So, that is the basic agenda of our 3 or 4 lectures on sequential circuit testing in this course. So, as we said that first our main goal today or in today's lecture will be to see how combinational circuit ATPG is different, or how sequential circuit ATPG is more complex compared to combinational circuit ATPG. That is what we will see. That is why we say that sequential versus combinational circuit ATPG and testing. What is the difference? That is, let us first study. So, if you look at this, look at the figure, this is the basic architecture of a digital circuit. So, here we have the next function block, which takes input as the primary inputs as well as the feedback from the flip flops. So, feedback from the flip flops we consider them as secondary inputs or virtual primary inputs, because they are not totally primary inputs, they are virtual, because they are actually feedback from the state registers or flip flops. The output of the next function block actually tells you which will be the next state of the circuit, which are also called secondary output, because the primary outputs will be output from the output function block, which we will see later. but the output of the next state function block NSF will tell you that this is your secondary output, because this is not directly output, but it is the secondary output which will determine the next state of the circuit. So, this is also sometimes called the next state bits of the circuit, and similarly the output of the state flip flops of the present state. So, we all know that from the digital design. So, this comprises this present state, and also they are actually feedback to the next state function block. So, we call them as virtual primary inputs or secondary inputs. Okay. And then there is a last block which is actually called the output function block, which takes as input the present state as well as the input. So, if it takes this input, we call it the milli machine, and if it does not take this primary inputs, only it depends on the next state, the present state. So, it is called the Moore machine. So, already we have studied them in the digital design. So, anyway, to make the things general, the output function block will take the primary inputs as well as the present state, and it will generate the primary outputs. Okay. So, I mean if you look at this block carefully, so we have 3 main blocks: next state function block, state flip flops and output function block. Okay. Among them, this is a combinational circuit, this is a combinational circuit block, and state flip flops are the sequential circuit blocks. Okay. So, now if you look at this from the sequential circuit basic block diagram from the combinational circuit point, so you can see that this is a combinational circuit, this is a combinational circuit. So, you could have done ATPG using or D algorithm or whatever we have learned, but there is a small problem here. So, in case of D algorithm or automatic test pattern generation by random test pattern generation, what you assume that in a circuit the primary inputs and the outputs are controllable and observable respectively. That is, you can apply some patterns in the primary output directly, and you can observe the patterns output directly. There is no need for extra circuit to control this inputs or observe the primary output. You may require some circuits to control intermediate lines, but we have again discarded that approach. But if you look at this very carefully, when your circuit will start up, so output of the flip flops are not known. Sometimes they can be 0, sometimes they can be 1, you do not know exactly what will be the value. So, we generally call them as X. Only you can control the primary input. Similarly, for the output function blocks, this set of inputs that corresponds to the state flip flop outputs are X. That is, they depend on what will be the value when your circuit starts. So, if you look at it, so this is a primary output, so very good. So, you can observe them directly, so there is not a problem, but you can control only half or 1/3 or a fixed fraction of your inputs of your circuit for this combination block and the output function block. Similarly, for this block, if you see, you can control this portion of your primary inputs for this next state function block, but the secondary inputs or the virtual primary inputs you cannot control it directly. Similarly, again another problem with this block is these outputs actually also you cannot directly observe, because they are going to be fed to the next flip flop, next bits, I mean as the inputs of the flip flop. So, this cannot be observed directly. Similarly, this cannot be not controlled directly. So, that is actually the difference. So, had it been a purely combinational circuit testing algorithm, then you should have been able to, there should have been a decoupling over here, there should have been a decoupling over here. So, you should have been directly able to control these points, and you should have been able to directly observe these points. Similarly, for this. So, as these things are not possible, so there is what we require. So, we require 2 extra steps, that is when you are going to test a sequential circuit, they are the 2 combinational blocks. So, I think you can directly use the combinational algorithms like ATPG, D algorithm and all, but with an extra constraint that somehow you should control them indirectly and somehow you should observe them indirectly. Similarly, for the output block you can observe directly for this part, no problem, but somehow you should control this indirectly. So, that is what is said. So, once achieved, then ATPG for these combinational blocks can be done by D algorithm. So, that is what we are going to see in today's lecture, how to do that. That is, we will apply D algorithm, but specially we have to control the virtual primary inputs, and somehow we have to observe the virtual primary outputs. This is what our job, then our job will be done. So, ATPG for sequential circuits will be same as ATPG of the combinational circuits. So, now we will see there are some assumptions which we will be taking. So, for virtual for ATPG of sequential circuit, that is some properties of the circuits we have to taken as assumption to make our algorithm simple, and on the same way. So, this set of assumptions actually apply for a very high fraction of the digital circuit which are being designed. So, we are actually targeting the majority of the designs. So, single clock sequential circuits we are taking, that our clock has single circuit and it is sequential. So, each flip flop has a 1 bit memory element, that is okay, obvious, and one common clock, that is one clock is being given to all the flip flops. So, all the flip flops switch in synchrony with the single clock. So, what it says that next assumption is after a clock edge, that you can say that we can assume that everything is working at the positive edge, that is your secondary primary output, that is your next state is transferred to the output of the flip flop, that is present state, and it becomes the new secondary outputs. Also the primary outputs are updated. This activity occurs at the clock edge, so it is called a synchronous operation. Basically what they have said is that, so there can be some input here. So now you give a positive clock, after the positive clock edge this output will come at this one, and it will happen for all the state flip flop in one go for this for the positive edge of the clock. So that is all changes, that is all changes in this, all changes we are actually calling secondary output. Secondary output will become secondary inputs at the positive edge of a clock, and this will happen for all the flip flops in this circuit. So it is called a synchronous operation. So that is what is the idea. Right. Next important point is that single stacked faults are assumed in the NSA block and the output block. So we assume that the stacked faults are at this nets, at these circuits, at the gates at this net, and also at the gate at this net. So I mean here you are actually having some, you can say some D flip flops are there. So DQ, some D or JQ or whatever, some flip flops are there. Generally in case of circuits we use D flip flops. So it assume that all the D flip flops are available in this state flip flops. Now what happens? We are saying that say this flip flop will be driven by some gate of this next state function block. So you can assume that there is a stack at 0 fault here and this stack at 1 fault over here. Similarly, this is driving some other gate in the output function block, okay. Also output function block or also some gate in the next state function block. So again you can have a stack at 0 fault and stack at 1 fault here. But internal to the D flip flops there are some other gates like feedback and all those things, as we all know the internal structure of a D flip flop. So it is assumed that the faults are not present in those internal gates. So I mean if you this second assumption says that stacked faults are at the output of the NSA block and output block, internal faults of the flip flops are not modeled. Their output and input faults are modeled, and faults of the input output signals of the combinational blocks. Okay. So that is what is being said that we model faults here, we also model faults here. That is the input pins of the flip flops and the output pins of the flip flops will have faults modeled, because you are considering flip flops, you are considering faults at the outputs of the gates of the NSA block as well as also the inputs of the gates at the output function block. Just like I have given an example. So some gate here will be driving this, which will have a fault, which you can think of having a fault. Similarly, there will be some gate whose input will be taken from here. So this will also you are considering as a fault. So faults at the input and output pins of the flip flop will be considered, but we are not considering the flip flop faults at the internal of the flip flop gates. So I mean this is to keep the thing simple, because if you start considering faults at the flip flop, then we can show that the circuit may not remain a sequential circuit at all. So it may one flip flop may start having multiple number of states, and all those much more complex modeling will come into picture. So the order of complexity will be very high. So in the very first few lecture we have said that what is the beauty of stacked fault model. So we are considering stacked fault model because it is simple to model, you can do collapsing and all, number of test patterns required are very less. At the same time they are giving you assurance that 99.9% cases, if you are assuming stacked fault, you can be assured 99% that there is no defect if your circuit does not have a stacked fault. The same thing logic also actually holds for a sequential circuit. If you consider faults only at the input and the output of the flip flops and forget about the internal faults of the flip flop, because if you consider faults at the internal of the flip flop, maybe your accuracy improvement will be 99.9999 plus 0.0001 plus 0.0001 may be there, but to improve that, the amount of complexity that will come into the algorithm will not make any help. Unnecessarily you will find that the circuit will have more number of states, the circuit may become a combinational circuit from a sequential circuit. To handle all these complexities, the ATPG algorithms will be so complex and the number of test patterns required may be so complex that we may lose what we are going to gain by adding this. So, and people have found out experimentally, just even if you forget the internal faults of a flip flop, still your coverage assurance or your assurance that if you cover the stacked faults there is no real defect, that assurance between this correlation between the stacked faults and the defects then is very high. So that is why we can assume that faults are only at the NSA block and output, and we can forget about internal faults of the flip flops. Okay. Similarly, no faults are considered at the clock, because if you find if you take faults at the clock, things will be very complex, like a sequential circuit may not be a combinational circuit. Some of the circuit may become asynchronous, because for some of the parts of the circuit clock may reach, for some part of the circuit clock may not reach, making it an asynchronous circuit, and the algorithm will be terribly complex. Okay. And they will also will not gain much in assurance level. So people have experimentally found out that you can forget about faults in the clock, you can also forget about faults in the internal gates of the flip flop, still the correlation between stacked faults and whatever you call the real defects are very high. So we will consider only flops in the inputs and outputs of the NSA block as well as the internal gates of the NSA block and the output block. And also mainly our as I told you, VLSI circuits are mainly consider what you called are the D flip flops rather than JK flip flop or J flip flop, because one flip flop can be converted to other flip flop, you all know. But in the case of digital circuits, we mainly consider about your D flip flops. So, in our assumption is that all the circuits will be taking henceforth are made up of D flip flop. Okay, so now again let us go to an example to tell what about the complex theories we are discussing. So, we may be lost. So, let us see the example of the complex circuit. I mean, it is a very simple example circuit. So, you can see that if you look at this is a simple sequential circuit. Now, you can see that this gate actually depends on the one input of the flip flop and the primary input, and it drives the primary output. So, it will become your output function block. You can map it to the old diagram and find out. So, what this gate belongs to? It depends on the primary input B, and also it depends on the output of the flip flop. This is actually the secondary input. So, you know that the block which depends on the secondary input as well as the primary input is called the next state function, and the output of the next state function block goes to the flip flop as input and will determine the next state. So, one actually is the output function block and this is the next state function block. If you just map it to this one, you will find out. So, let us consider as a flop false stuck at 0 at one input of your output function block. So, now let us see how you can do the testing. Okay. So, this is the case. So, only you have to remember that this is the output function block and 2 is the next state block. Okay. So, now when the circuit starts up, as you all know that initially all the gates, all the nets are having a value of x as per D algorithm. So, now this is stuck at 0. So, you have to apply a 1. So, it will be D. Okay. Now, one thing is that, so there is actually this is the D. So, there is only one path through which the fault effect can be propagated, that is actually called a singular D path. So, you have to fault effect should be there. So, our target is that, so gate 1 is in the D frontier because one input is D and the other output is X. So, and there is only one path through which the fault can be propagated, this is called the singular D path. So, this should be at D after propagation of the fault effect. Again now it may one may be now it is D, output is D. So, this F is unknown X. So, by the J frontier algorithm or J frontier concept, we know that F has to be a 0 for the fault effect to be propagated. So, we require that one. But now you can see because the circuit, because now you cannot directly control F, that is the difference between a sequential circuit testing as well as a combinational circuit testing. Had it been a combinational circuit, then what would have been done? F could have been directly controlled and you could have applied 0 at there. But now it is not directly controllable because it is the output of a flip flop, and the output of a flip flop will totally depend on what is the value when it gets started. So, now it is X. So, we require it to be a 0, but now it is at X. So, we are in a problem because we do not know how to make it this one. So, we have to now do something so that we get F equal to 0, and once F is equal to 0, then you can apply this one to get this, get the fault tested. So, our main job is now to get a 0 at F. So, actually it is called indirectly control of F to 0 because you cannot directly do this one. So, how can you do that? Let us say that we put B equal to 0. So, if B equal to 0, this is X, okay, because output. So, if you apply B equal to 0, then irrespective of what is the X can be 0 or 1, we do not know whatever, it already told you the X means either 0 or 1, we do not know because on the power half of the circuit we can have any value at X. So, even if it is 0 or 1, whatever may be the case, but if you put 0, so D will be a 0. Now, you put B equal to 0, X I do not bother at the time being, and you apply a positive edge of the clock. So, once you do this 0 will be coming over here, right. So, you apply a B equal to 0 and you get a 0 and apply a clock pulse. So, once that is done, so what you are going to get? You are going to get a 0 over here, going to get a 0 over here. Now, you indirectly have made F equal to 0. Now, you can put A equal to 1, B you can totally forget for the time being, and then you will get this value of the output and circuit tested. So, now in case of sequential combinational circuits, what we have seen that only one pattern can test your fault, correct. So, you find out by the sensitized propagator justify or whatever by a random pattern or not, but one test pattern can detect directly whether there is a fault in the circuit or not. But in this case we require two patterns, as you can see. First, we have to apply A x B 0, A is we do not know, B equal to 0. So, which will make that F equal to 0 indirectly. So, once F is equal to 0, now you apply A equal to 1 and B equal to x, so that your circuit gets tested. So, this is the basic fundamental difference between sequential circuit testing and combinational circuit testing. So, in sequential circuit testing what we have done? So, in sequential circuit testing we require that first the virtual primary outputs or secondary inputs whatever you the virtual primary inputs or secondary inputs whatever you call, they have to be indirectly controlled because they are the outputs of the flip flops, that they have to be indirectly controlled to some value that is required for ATPG. So, you may in this case there is only one flip flop, so you require only one step. So, slowly we will see how many steps are required to make the secondary inputs controllable. So, you require one pattern, one clock, then one pattern and a clock, some amount of patterns and a clock. So, in this case there is only one pattern required and a clock has to be applied. So, it will virtually or indirectly control your virtual inputs. Now, once the virtual inputs are controlled, then you can directly control your primary inputs and then you can see what is the ATPG is done. So, in this case we require two patterns to do it. Okay, now let us see that, but in this case if you are we consider a fault in this next state function block, this was NSF. So, in case of this was the output function block, this was the output function block. So, we consider a fault here. So, somehow we required to control this net to 0. So, we have done this indirectly, but the output was directly observable. So, we could have done this in two patterns. But now, we will take another fault in this block, which is actually your next state function block. So, here life is bit more difficult because you have to directly control this indirectly control this secondary input, as well as the output of the next state function block is not directly observable. So, you have to somehow make it indirectly observable. So, testing faults at the next state function block is somewhat more complex than your what you call this output function block, because in case of output function block the primary output is directly observable, but in this case it is not. So, stack at one fault. So, what do you require for stack at one fault? So, obviously you require a 0 over here, correct. So, now this requires a 0 means it is d prime over here. So, but to get a d prime over here, so you have to get a 0 over here, but as you know this is the output of a flip flop. So, we have to do that indirectly. So, how you can do that indirectly? So, you do not forget about x a, the b you put as 0. So, irrespective of everything you get a 0 over here and then you get a clock pulse. So, once you do this you will get this as a 0 over here. So, this is what is being done. So, if you make b equal to 0, apply a clock pulse, then you get x equal to 0 and your fault gets sensitized. This is what you do in the first step, this indirect control, correct. So, you get this one. Now, next thing what you have to run, so you get a d prime over here. So, now what you know, so you have fault is sensitized. So, previous case b equal to 0 was the previous case. So, now what you have to do, so you know that if this is the fault, this is the only AND gate. So, therefore, this becomes the frontier and a unique d frontier, or there is only a unique x path in this case. So, you have to somehow propagate the value of d prime over here. So, for that you require to have a 1 over here. So, in the next stage what you do, you forget about x, make b equal to 1 and then, so it will be a 1. So, this d bar will be floated over here and then you give a clock pulse. So, once you give a clock pulse over there, so d prime will appear at the output. Now, you have to observe that even if d prime has come to the output d, that is the virtual primary output, but still you cannot observe it directly, unlike your next state function block, because it is going to the input of a d flip flop. So, that is why more complex faults to be tested in the what you call the output function blocks. Faults which are in faults which are in the next state function block is more difficult to be tested, because not only you have to indirectly control some lines, but also have to indirectly observe some lines, which was not in the case of gate 1, which is the output function block. So, somehow you have brought this here, but now you cannot observe it directly. So, you have to somehow make this d prime appear over here. So, you have to go to the third step. So, last we could have done everything in the two steps, in which first we controlled f to some value and then fault effect was propagated here. But now, in this case 3 steps are required. First you sensitize this to 0, then we propagated the fault value to here, and then as this is not directly observable, somehow you have to bring this value to here. So, next stage, so in the second part what we have done, so we got this one. So, second stage what we have done, so it is 0, so it is 1. So, this fault effect from here it has come over here. Now, you apply a clock pulse. So, if you apply a clock pulse over here, your third state, you apply a clock pulse over here. So, your d prime will come here. So, now your d prime is here. Okay. So, that is in the third phase you get a d prime over here, but now again this has to be observed by this one. So, you have to make a equal to 0. So, we are indirectly applying 3 clock pulses. If you see, first a equal to x, b equal to 0. So, indirectly you are controlling this value, this one. Next you are applying a x equal to 1, x equal to 1, b equal to 0. So, your fault effect is propagating to the output, but the output is cannot observe. So, third step what we do, again we put a clock edge, so that it comes out indirectly via your primary output. So, that is a more difficult if you are considering faults at the next state function block compared to output function block. But for all the cases, unlike combinational circuit, you have to indirectly control virtual secondary inputs and indirectly observe the secondary outputs. That is what is the basic conceptual difference. So, in case of sequential circuit, more than one test patterns may be required to test a fault. So, indirectly, so broadly speaking, the complexity of sequential circuit testing is is more difficult compared to a combinational circuit testing. So, in this case, you have to observe that we are not considering the cases where there can be inconsistency and when there can be a backtrack. So, you can understand that how the complexity will blow up if you start considering this. So, we may use D algorithm to find out that this can be a good path of propagation and all. So, now instead of one pattern, we have generated 10 or 20 patterns which are required to indirectly control these virtual inputs and indirectly observe the virtual outputs. But now after that, you could have found out that for some step there is an inconsistency and we have to do a lot of backtracking. So, in combinational circuit there was only one pattern for a fault, but now there are 10 patterns or 11 patterns or x number of patterns for a fault. So, again if you remember that there is a backtrack in the final phase, so how much amount of computational work has been lost. So, that is why sequential circuit testing is highly more complex than a combinational circuit. So, that is what we are going to focus today, and in the next class we will see how we can solve this complexity. Okay, so now we will see that what kind of algebra, like in Roth's 5 value algebra we have seen for combinational circuits, but now we are going to study here that do we require some extra kind of logic or extra kind of algebra. We are asking the question that whether some extra kind of logic is required for ATPG for sequential circuit, or whether 5 valued logic would suffice or not. So, let us just see that we will try to use a 5 valued logic and see what is the gain and what is the loss, and then we will try to see if we can go for a higher order logic. Okay. So, let us see that this is the circuit. So, there is a stacked 1 fault. So, obviously stacked 1 fault over here. There is a stacked 1 fault over here. So, a stacked 1 fault here means you have to apply a 0 over here. So, now there is 2 paths. So, one path is this fault can be propagated here and other path can be here. So, there are 2 x paths here. So, for the time being let us see that if this path is smaller. So, by any heuristic if you apply over D algorithm. So, we can take that E and F may be a very good path to propagate the fault, because the other path like E, D and G is the longer path. Correct. So, stacked 0 0 means it will be a D prime over here. So, you can propagate the value of D prime over here, D prime over here. But immediately we know that D has to be a 0 over here. So, how do we get a 0 over here? So, we know that directly we cannot get a 0 over here. So, better what we can do is so how do we get a 0 over here? So, what we can do so net D, actually already told that net D is not directly controllable. Okay, so, we have to make this net D equal to 0, because actually this net depends on a output of a flip flop. So, this gate is not directly connected to the output of a flip flop, but is indirectly dependent on net C, which is the output of a flip flop. So, indirectly you have to control this D to 0. So, if you just look at it, we can very easily do that. You can make A equal to 0. So, if you just make A equal to 0, now what you do? You give a clock pulse. So, just if you give a clock pulse A equal to 0, then this one will come here, and this is x. So, x and a 0 will be a 0, correct. That is what is our idea. So, this is how we were doing by a D algorithm. So, just let us quickly see once more what we have done. So, this is the fault stacked 1. So, we apply a 0 over here. We need to apply over a 0, and this is the path propagation. So, we may get a D prime over here. So, this is the path, and to get this one we require a D over here. So, D has to be a 0 over here to get the fault this one, but now D is not directly connected to the output of a flip flop, but it is connected to C, which is the output of a D flip flop, and this can be directly controllable. C, you may note that it is nothing but a secondary output, because it is the output of a flip flop, not directly controllable. So, somehow you have to make this to be 0. So, if you want to make this one to be 0, because you want D to be 0, so somehow you have to make this to be 0, because we know that 0x is a singular cover. So, to make x equal to 0, what we can do? We have to make A equal to 0 and give a clock pulse. So, immediately D will be equal to 0 and your D prime will be propagated to the output. So, what are the 2 test patterns to test the fault? One test pattern is A is 0, B x, and the next pattern is A x and B 0. So, this will test your fault. So, there are 2 patterns required to test the fault. Now, let us just do a side trick of Boolean algebra and see can we achieve something better. Okay. So, let us for totally just see this one and forget about all this. So, we can keep it as an x for the time being, keep it as an x. Okay. Now, let us see what we can do. So, let us see it is stacked 1 and we apply a 0. So, normal case 0, fault case 1 we can write like this, correct. So, now in this case you can see that this is also D prime. So, we just write all this we require, correct. this is what we require, something over here, and here we write it also 0/1. Now, just have a very quick look at the circuit. Just just look at this point. So, this point is very important, this net, just net E, if you look very carefully. So, what is the idea? So, if just net D is 0 and a 1. Now, let us look, sorry, net E is directly, you can net details about net E you can directly get from this net, because it is the fan out for this step. Now, let us look at net D very carefully. So, net D is in fact x by D algorithm or Rouse's 5 value algebra. Now, you can see, because one value is x and 0 1. So, if you do something like this, so you can will get 0 and x kind of a thing, you will get at the output. Okay. So, but 0 and x is not a part of your Rouse's algebra. So, let us see. So, in this case, so we get D equal to 0 1 and this is an x. But now, look at D very carefully. So, now what happens? Say let us forget about this being 0, let us assume that it is x, we do not know the output of this one. So, if fault is not there, so what if fault is not there? So, what is the input over here? It is a 0. Okay. And what is the value of this? It is x, because we are not we do not know the case normal or fault, because we do not know the output of this one. So, what is the output of D at fault? So, if the fault is not there normal, so the output will be a 0, because if the fault is not there, stacked fault is not there, so you apply a 0 over here, so you will get a 0 over here. So, default your D is going to be a 0, okay, and other things are fine. Now, if there is a fault, then what will be the case? If there is a fault, then it is stuck at 1, so you are going to get a 1 over here, and this is a x, because we are not applying anything for the time being, just assume. So, it will be a x. So, it is 0 and x at D if you are not controlling this, for the time being, just assume, correct. So, now the output of E is D prime, that is 0/1, and D you can write as 0/x. If the fault is not there, you apply a 0, so the output will be 0. But if the fault, stuck at 1 fault is there, you do not know what is the output, so it can be a x. Now, you just and f we know is 0 1. So, if you do a ORing of this one, so the output of G is what? So, it is 0 or 0 is 0, 1 or x is a 1, which is nothing but a D prime. So, it is very surprising cases happened here, that even without controlling this guy to 0 or this guy to 0 indirectly, which is required in the D algorithm or Rouse's 5 value algebra. So, if you have a element in this, which we are calling it as 0/x, because if you remember Rouse's algebra, there is no concept of 0/x. We have x/x, 0 1, 1 0, 0 0, 0 1, sorry 0 0, normal 0, fault 0, 1 1, normal 1, fault 1, x we do not know, 0 1 that is D prime, 1 0 that is D, but we do not have any concept of 0/x. But if you have a concept of 0/x, then only one pattern can detect this fault. This is a very special case, in which case I mean it is not required for control and all, but most of the times we may have to require this. But for some of the circuits you can find out that if you have the concept of 0, that is point D is 0/x, then only one pattern, x A equal to x and B equal to 0 will test your circuit. But if you are directly following D algebra, that is we do not have any concept, that is there is only one that is in the Rouse's 5 value algebra, there is only one concept, that it is x. So, x means it is xx. So, it is x, that means it is xx, so it is also xx, something like this. You cannot write 0/x or x/0. So, in that case, if you directly follow the D algebra, so you require one pattern, this one, to make this D equal to 0, and then you require another pattern to propagate the fault value. But if you write if you have there is a concept of writing 0/x, which is basically the case, because if the circuit fault is there, then only the output is not known, which will be dependent on the virtual primary output, that is D. But if the fault is there, if the fault is not there, then you apply a 0. So, it at all does not dependent on the output of the flip flop, that is does not at all dependent on the virtual primary output or the secondary output, then you get the value 0 directly. And by doing this thing, you can get a D prime over here without controlling this. So, this is a very special case of an example where you can test a circuit in a sequential circuit without requirement of controlling the secondary primary output, because of the fact. But now, for that you require some special symbols, which we are this was about the theory which we are discussing, that higher order algebra we require a symbol like 0x and all these things. So, higher order algebra are many advantages, we will come back. So, by adding one extra symbol, that is actually 0/x, we got that in case of a sequential ATPG only one pattern or at least one level of computation was less required. So, 9 valued algebra are used in sequential circuit, that is 0, 1, x, d and d prime. These are all from Rao's 5 value algebra. But now we have added some more 0 x, that is normal case 0, fault case unknown, g1 normal case 1, fault case unknown, f0 normal case x, fault case 0, normal f1 is normal case unknown, fault case 1. So, with this addition of these things, you can see that for many times you will be requiring less amount of computation to solve your problem. So, that is what is required in the last example, higher order algebra, this one. So, which is required to reduce the number of computation, or only one test pattern can do it, and it is not available in a 5 valued algebra. So, that is why we sometimes require to go for a higher order algebra, that is 9 value algebra. So, higher order algebra improves the efficiency of sequential circuit testing, because you require less number of tests for the computation. But only one thing you have to observe, that always it will not be possible to even if you are using a 9 valued algebra, that directly you do not require to indirectly control any virtual primary outputs or virtual primary inputs kind of a thing. So, this was a special case where it happened, but only you can assume that, or it has been found out experimentally, that if you are using higher order algebra, then the number of computation generally reduces, because you have some more flexibility like x0, 1 x, 0 x, 1 x, something like this. So, more the number of x's in the circuit, we have seen that more number of flexibility is there. So, that is why it will improve your efficiency, because in case of combinational circuit testing, one pattern was used to detect this test, and but here you require more than one pattern. So, a lot of computations are required. So, we want to have more flexibility in this circuit. So, you are using some other higher order algebra. So, you can also question me that higher order algebra would have also helped in combinational circuit. The answer is true, because in the last lecture with an example we have shown that if you have more number of x's in your circuit, then it is true that there will be more number of flexibility, and ATPG may succeed better. So, if you have 9 valued algebra in combinational circuit, you are correct, you will get better solution. But having a 9 order algebra is also computationally difficult, and it has been found out that the amount of gain you are going to get by using a 9 valued algebra is not that much in a combinational circuit by the amount of inconsistency that you may reduce. That is because in sequential circuit there are more number of test patterns, more number of patterns are required to find out a test pattern. So, we want more flexibility. So, you use this extra 4 symbols like 0x, x0 and all these things. But same thing if you bring out in a combinational circuit and make it 9 value algebra for combinational circuits, so some advantage you will get, that is definitely, because more number of x's will be there in the circuit. But the amount of complexity you will incur there will not help you to gain, because in combinational circuit one pattern is enough to detect a circuit. So, I mean inconsistencies are a bit more less compared to sequential circuits. So, that is what, that is what about the higher order algebra, and we have seen the motivation. So, now what we are going to do, so we are going to see ATPG for sequential circuits using time frame expansion method. That is like D algorithm we have seen. So, in D algorithm what was the idea? That is a formal algorithm to find out the test pattern for a combinational circuit. So, in this case this time frame expansion method is another formal method for what you can say, it is a very formal method like D algorithm which can find out test patterns for sequential circuit. So, let us see this in details with an example. So, what is the first step? Replace all the flip flops by nets. So, first there will be sequential circuits will be there. So, there will be some flip flops over will be there. So, as purely sequential circuit is a singular clock is the assumption. So, then you remove all the flip flops, that is the first job, and perform D algorithm on the virtual combinational circuit. So, whenever if you remove the flip flops, so what will happen? The output of the flip flops will become your virtual primary inputs and your that is what. So, we know that, and the outputs of your and the inputs of the flip flop will become your virtual primary output. See what we have done, we are removing all the flip flops. So, if you remove all the flip flops, what will happen? The outputs of the flip flop will become virtual primary inputs. Now, you can also consider them as inputs, and the outputs of your and the inputs of your flip flop will become the virtual primary output. So, some changes will there which you will see in the example, that is what is going to happen. So, virtually you are going to get a combinational circuit. Now, you use D algorithm on that, and you will have to use, so this step 2, you have to do multiple steps we will be requiring to control the secondary inputs and observe the secondary output. So, already we have seen that this will be that for controlling the virtual primary inputs and observing the virtual primary outputs you may require multiple steps. So, that may be required, but let us see with an example, because that was a mathematical definition kind of a thing. So, let this be your circuit to be tested, and we have a fault over here. So, there are 2 flip flops. So, you can consider this as your virtual secondary input, because it is the output of a flip flop, this is secondary input you can say. Similarly, you can also see this is the output of the flip flop, this is also a secondary input, because you cannot control this direct. secondary input, yeah, you cannot observe this directly, correct. Now, this is one input to the flip flop and this is a special case. So, this is a primary input as well as the input to the flip flop. So, you can say that this is also both a primary input as well as a virtual input, and but in this case you can see that this is the output of this gate is going to the input of this gate. So, this is actually a virtual input. This is virtual primary input or secondary input, because you cannot control this directly. That is what is our idea. So, this is virtually primary input, this is virtually primary output, you can say, or secondary output. Similarly, this is output of the flip flop, but you cannot see that directly. So, you can consider that this virtual primary output kind of a thing. Okay. So, that is what is our idea. And also you can say that this is again going to the input of another gate, because this is also this output as well as it is, had it been directly coming out, then we could have called it a virtual primary output, because or a primary output, something like that. But you can see that also it is going as an input to another gate. So, that can also be, cannot be directly controlled or observed. So, you can say that this is a virtual primary input or a virtual primary output, that is secondary input output. So, it is not directly observable, not directly controllable. So, somehow we have to do this indirectly. Okay. So, you can easily map these gates to which is the NSF block and which is the output function block, that can be easily done. But anyway, that is not much of a concern right now. So, this is a stacked fault over here. So, what is the first step? First step is remove the flip flop. So, you have removed this flip flop here, you have removed the flip flop here, and then we have shorted this. So, this is what is your idea. One thing is to be remembered, that you cannot control this directly, and also you cannot control this directly. That is, even if this is connection over there, if you want a 0 say, or if you want a 1 over here say, you apply a 1 1 or 1 here, you cannot get the 1 here directly, because it is cut by a flip flop. That assumption you have to know, that similarly you cannot get a 0 here directly or 1 here directly, not possible, even if we have shorted this. So, that is has to be remembered. So, but it is now a, so but for the D algorithm, for next step is that is now, but with this small assumption in mind, that is not a very explicit assumption here. So, what we have seen, that is not a very explicit assumption, but we just know in our mind that direct cannot be controlled or observed. Now, this is a virtual combinational circuit, that was I was saying, that is a virtual combinational circuit. Now, in the virtual combinational circuit, you apply combinational D algorithm, that is it. So, now you just see what is the combinational D algorithm over here. So, we know that with a 0, so you have to apply a 1 here. So, it is a D over here. So, you have to propagate it. So, it will be a D. Now, the other input should be a 0 or gate, this is a 1 here you require, and next is that you have to apply a 1 over here. So, apply a 1 over here means A has to be a 1 and this input also has to be a 1, correct. Next, what is the case? So, this has to be a 1, so the output has to be a 1. So, 1 means the AND gate, this has to be a 1. So, if you apply a D algorithm, so you could have directly said that A1, B1 and C1 if you give, and the output is the, so your circuit would have been directly tested if it is a combination circuit. But here is a big but over here. So, you require a 1 over here, you require a 1 over here. But as I already told you that internally you have to remember this big but, that this directly not controllable, this also not directly controllable. That is a big but you have to remember. So, how you can get a 1 over here, you have to do that indirectly. Similarly, how to get a 1 over here, that also you have to do indirectly, because these two are output of the flip flops which are going to your input of some gates. So, they are your virtual primary input, they are not your direct primary input, they are your virtual primary inputs and you have to control them virtually, that is the idea. Similarly, if somebody needs to observe this, that also not be possible, because they are either internals, or you can also, even if they are feeding it to some outputs of the flip flops, or even if they are going as an input to the output function block, they cannot be done directly because of this virtual primary output and virtual primary input kind of the behavior. So, now let us forget about this. So, I mean let us see what is our target. So, our target is that this we have to apply eventually to do this, but before that we require a 1 over here, because we require a 1 over here. For that we require a 1 over here. Similarly, that is done. So, this is our requirement number 1, this is our requirement number 2, okay. And once this requirement is done, so you get a 1 over, this is not your immediate requirement. So, this is your requirement number 1, this is your requirement number 2. So, if you can get a 1 over here, if you can get a 1 over this point, then your circuit testing is done by applying this. So, somehow you should get these two things indirectly. So, that is it saying. So, this one is your input pattern. A1 can be applied directly, but D equal to 1 and I equal to 1, D equal to 1 I have to do by some other mechanism. So, that is what is very much required, and we will see how to do that by time frame expansion method. Okay, now, so just two very simple definition. So, one is called the sequential depth of a flip flop. So, the output of a flip flop can be controlled by only primary inputs and clock pulse, then it is sequential depth of 1. That is, just look at this flip flop. So, it can be controlled directly by the primary input. So, its depth is 1. Now, if you look at this flip flop, so it depends on what? It depends on this input line E, which is again dependent on this flip flop, which is having a this flip flop is dependent on, sorry. So, this flip flop actually is dependent on this input, correct, and this input is dependent on the output of another flip flop. So, and this is having a sequential depth of 1 because it is directly controlled by the primary input. So, depth of this one will be equal to 2. So, what is the definition? Just if you look at it. So, if the output of a sequential flip flop is direct, this is 1. Then the circuit of figure, last figure if you take, then this is a sequential depth of 1 and is directly controlled by C. That is what. So, directly controlled by C, so depth is 1. Now, this flip flop is saying that a flip flop has sequential depth D sequence if its output is dependent on primary inputs and at least one flip flop of depth n minus 1. So, that is you have a flip flop here. So, this input is dependent on a flip flop, depth of is D sequence minus 1 and some other primary inputs it can be there. Okay. So, that is indirectly this is a flip flop whose input is dependent on another flip flop whose sequential depth is D sequence minus 1, then you have to add a 1 for this flip flop and it will be D sequence. So, that is what. So, first flip flop you consider which is dependent on directly primary inputs, that will be value 1. Then you find out the next set of flip flops which is dependent on primary inputs and all those flip flops whose sequential depth is 1. So, their value will be 2 and you can keep on doing it. So, in our example this is having a depth 1 and this is having a depth 2. So, that is the next definition we have got, correct. So, now there is a definition of a cyclic circuit. So, what is a cyclic? So, this definition says that a sequential circuit is non-cyclic if there is no flip flop whose primary input is dependent on its output. For example, if you consider this circuit, this is a sequential circuit because its output is dependent on its, this one, you just look at the feedback. So, its output is dependent on its own input. So, that is actually a cyclic definition, but if you look at this flip flop, this is not a cyclic, this one because this input is not dependent on this output. So, that is the definition of a sequential what you call cyclic circuit. Okay. So, non-cyclic circuit means the output of the input of the flip flop should not depend on its output. This one, so this circuit is not definition. So, this is a cyclic circuit and the other example is a non-cyclic circuit. So, now we are going to very quickly see a property. So, this time frame expansion is a property, this property. The secondary output is if the circuit is cycle free, okay, if the cycle is having a, if the circuit is having a cycle, then we will see in the end that no testing can be done or it is very difficult to do testing for that kind of a circuit because it will be there will be continuous oscillations. Like in this case the output is dependent on its own input, the input is dependent on its own output and there will be oscillation and you cannot control any value. So, circuit faults cannot be tested in that circuit or it is very difficult to do that. But we will see that, but for the circuits where there is no such cyclic property, then what we can do is that we can control all the virtual primary inputs and observe all the virtual primary outputs. That is the property is saying the secondary outputs, that is your virtual primary inputs, the secondary inputs, that is your virtual primary inputs of a cycle free sequential circuit, depth this one, can be brought under control in at most like this one in D sequence number of primary input and clock pulses. So, what we are seeing in the last few examples that we require some nets, like in this case if you look at it. So, we require to control these two 1 and also these two 1. So, now we can ask that how many clock pulses and patterns will be required to do this. The property says that if the maximum depth is 2, so you can do it in 2 clock pulses and 2 inputs. Now, how it can be done? It is very simple, the idea is very simple because this is sequential depth 1. So, sequential depth 1 means what? It is directly connected to a primary input or a set of primary inputs. So, give some whatever pattern is required at the output this, in this case it is a 1. So, you can apply a 1 in C and 1 clock pulse will directly set it. That is, in other words, all the what you can call all these flip flops which are in sequential depth 1 can be directly controlled by setting the primary inputs and apply a clock 1 because they are directly dependent on the primary inputs. Now, after 1 clock pulse and 1 pattern, all the sequentials, all the flip flops of sequential depth 1 has been set. Now, you can consider for the flip flops in sequential depth 2. So, now we know that after 1 clock pulse 1 pattern, all the flops having a sequential depth 1 has been set. Now, flip flops with sequential depth 2 are dependent on what? Primary inputs and outputs of flip flops which are sequential depth 1. So, now indirectly you can say that one more pattern and one more clock pulse will set it, because after one pattern this guy is set because he is sequential depth 1, and this guy is dependent on primary inputs and only on this output, that is only on flip flops whose sequential depth is 1 because the sequential depth is 2. So, now you can apply another clock pulse and this value will be at the output. So, by second clock pulse all the flip flops having a what you call sequential depth 2 will be set. Similarly, if you have a sequential depth flop with 3, then you have to have a third clock pulse, because by second clock pulse all the primary inputs you can set it, and all the flip flops having sequential depth 2 has been set by the second clock pulse. Now, in the third clock pulse all the flip flops or sequential elements with depth 3 will be set, because in the second pulse all its inputs are ready, because the inputs of a flop with a sequential depth 3 are flops with sequential depth 2, which has already been set in the clock pulse 2. So, another clock pulse you apply, your third level flops or sequential depth third flop will be set, and so on. So, the proof is very obvious, which we have discussed, and we can see this pictorially this way. This is the sequential circuit of depth 1. So, it is a combinational circuit. So, primary clock you apply a clock, this is set. For the depth 2, now in depth 1 in first clock pulse it has been set. Now, in the depth 2 you require another clock pulse, because now because in first phase all this is set, and in case of the second in case of the flops with depth level of 2, all the flip flops with depth 1 has already been set. So, just you apply another clock pulse and this output will be controlled. Similarly, dot dot dot. Now, if there is another flip flop whose depth is 3, you require the third pulse, because by the second clock pulse all the flops of depth 2 has been set, and flop with level 3 are dependent on the output of the flops with gate 2. So, a third clock pulse is required. So, very obviously it is said that the secondary inputs of cycle free sequential circuits of depth this can be brought under control in at most D sequential primary inputs and a clock pattern. So, therefore, if you have a circuit with 10 flip flops or having sequential depth 10, so you require 10 clock pulses and 10 patterns to set the virtual primary inputs, and in the 11th period you require to give the primary inputs, and that will solve your problem. Okay. So, again coming back with this property, we will see how this time frame expansion method can be applied to the circuit. So, you know that this is a stuck at 0 fault over there, sequential depth was 2. So, here we require 2 patterns to bring, we have already seen that we require a 1 over here, we require a 1 over here, correct, to do this testing, because we are going to apply a 1 and this will be D, this will be D, we require a 0 over here, we require a 1 over here, we require a 1 over here, 1 1, this is also required a 1 over here, 1 over here, 1 over, something like this you have already seen. So, this we need to control to 1 and this we need to control to 1. So, and sequential depth is 2. So, you will require 2 clock periods to make this one to 1 and this one to 1. And finally, you have to apply A equal to 1, B equal to 1 and C equal to 1 to test the fault. So, let us see that explicitly how it can be done. So, 2 patterns to set and the third pattern to test it. So, what we do? So, first, so this is what is the case. So, you require this is the test pattern, as I told, you require a D equal to 1, I equal to 1 to do this testing. So, we require to control this at level 1 clock, because this is level 1 flop, and this we require to do at the second clock pulse, because this is the level 2 clock. So, this is what is required. Now, you see this is time step 1. So, how to do that? So, time step 1 what we do? We require a 1 over here. So, what we do? We make C equal to 1, others we do not require at this at all, and we apply a clock pulse. So, what is going to happen? We are going to get D equal to here. So, this you can think that your clock pulse is set, okay, right. So, this is what we have done in the step 1. Other primary inputs are do not care, finally a clock pulse is given, C equal to 1 is required, that is shown. So, we do this, so we get a 1 over here and it is done. Now, you see, now, so what is happening now? So, you can know that now D equal to 1 already, and this is X, this is X, we require a 1 over here, this is very important, that is second phase we want, okay. So, this is requirement, this is already done. Now, what we have to do? So, now we require a 1 over here, and if we apply a clock pulse, then we can get it a 1 over here, because what this is already done in the last phase. So, now what we have to get a 1 over here, what we do need? We need a 1 over here and we need a 1 over here. So, 1 over here is already done in the last step. So, if we apply a 1 and a 1 over here and we apply the second clock edge, then what is happen? This 1 will be reflected over here. But one more point we have to remember that this 1 and a 1 will be reflected over here, but the same clock is going here and same clock is going here. So, it is not that if you want to transfer this from here to apply, you apply a clock over here and the clock is not coming here, the clock will also be coming over here. So, you have to be very careful that when this one and this one together with this one is transferred over here. So, this should remain a 1, because in the end of second phase we require a 1 over here and a 1 over here. So, you apply a 1 over here. So, what we have done? So, indirectly what we have done over here is the first phase we have a 1 over here, in the second clock pulse we put a 1 over here. So, 1 and a 1 you get a 1. So, if this I just apply the clock pulse you will get this one, but you have to be very careful that after the second clock pulse also 1 is to be here. So, we also put C equal to 1. Now, we apply a clock pulse, same clock pulse will go both. So, 1 and a 1 will be coming over here and we 1. So, this 1 will be maintained over here. So, now you get after the second clock pulse we get a 1 here, a 1 here. So, this 1 1, so you get a 0 over here and a 1 over a 0 over here, that is this is what we are getting after the second clock edge. We get a 1 over here, we get a 1 over here, okay, we get a 1 over here and a 0 over here. So, this is what we have got after your second clock pulse. And the time step 3, finally you have to apply the clock pattern and you will be done. So, you are getting a 1 over here, you are getting a 1 over here, that is already done in the first 2 steps. So, now what we require? We require a 1 over here, that you will get a D, then you have to propagate this should be a 0, okay, and this should be a 1. And you can do the testing. So, to do this what you require? To get a 1 over here, you require a 1 over here, that is already set by this which was virtual primary input. So, we have already set by the clock pulses, you just apply B equal to 1. So, you will get a 1 over here, a 0 over here and this is done. So, now also you require a 1 over here to sensitize the fault. So, for that this is 1 which you already set using 2 clock pulses because this was a virtual primary input and A is a primary input. So, you want to 1 here. So, you apply a equal to 1 over here, you get, and this is done. C equal to x, you do not require this. So, 3 clock periods. So, first you apply C equal to 1, set this as 1. Second clock pulse you apply B equal to 1, C equal to 1, B equal to 1 and C equal to 1. So, you set this one. And third clock pulse you apply B equal to 1, A equal to C, you do not care and you do the testing. So, that is what we have done. This is actually called a time frame expansion method, because in 3 clock periods we have tested the circuit. In the first 2 clock periods what we have done? We have set the non-primary inputs or the virtual primary inputs or secondary inputs to 1 and a 1, and in the third clock pulse we applied the primary inputs and the testing has been done. So, if I want to illustrate this as a figure, so this is what is being done. So, if there are if the sequential depth is D, then we require one time frame which we call minus D, then we actually called minus D plus 1 dot 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 till D. So, in this case we had a frame sequential depth of 2. So, this was actually 2 minus 1 is equal to depth 1, then this will be depth 0 and this is actually depth 1 kind of a thing. Okay, so, it is so our sequential depth was 2, so it was minus 2, then minus D was 2 in this case, so it was minus 2, then minus 2 plus 1, that is 1, and the finally it was 0. So, finally applied A equal to 1, B equal to 1 which we did the testing. In this case we applied C equal to 1 which set the value first output of the first flip flop to 1, and in this case we applied B equal to 0 and C equal to 0, then it actually set the value of the next flip flop to 1, and finally we applied this pattern and we did the testing. That is how we represent this circuit. I mean, this is a way of representing your time frame expansion method. That is, we replace the flip flops with replaced by nets. So, flip flops are eliminated. So, this is what we do, and this is your secondary inputs, not the primary inputs, this is your secondary outputs, and this is how we represent, this is your primary inputs and this is how we control. So, now just whatever we discussed in that, so let us just put it in the time frame method and see what we have done. So, this was your circuit, if you remember, this part of the circuit we have just drawn in a horizontal way. This circuit we have drawn in a horizontal way, a vertical way, and these things had been shorted, and this thing has been shorted. That is the only thing we have done. So, just see, this is your flip flop, this has been entered. So, let us just mark this as, say we can call it gate number 1 and gate number 2. So, just you have to remember that input of gate 1 is B and D, and input of gate number 2 is I and A, but this I is actually a virtual input and this D is fine, and this for this case D is a virtual input. So, you can just see what we have done. This is, say we can think that see, so this gate is this gate is 1 and this gate is 2 kind of a thing. So, you see one gate 1 it is directly connected from A, this is gate 2 and this is gate 1, this is gate 2 and this is gate 1, this is gate 2, gate 1, gate 2, gate 1. Okay. So, see this gate 2 is dependent on A and the output of this second flip flop. So, this is how we represent it. So, this gate 2 is dependent on A, that is primary input, and output of the second flip flop, that is right F2, and gate 1 if you remember was dependent on B as well as the output of the first flip flop. So, this is your gate 2, this is your gate 2. So, it is dependent on B as well as the output of the first flip flop. Okay. So, this is how it is done. So, now you can call this 1, 2, this can be called as 4, this can be called as 3. So, this can be called as 4, this can be 3 or whatever you like. These are not that much important, this only thing is important. So, gate 1 is dependent on B and the output of the first flip flop. Gate 2 is dependent on A and this one. So, we write it this way, and this is stuck at fault 0. So, we write this, you see about a D algebra which you have written, extended D algebra. So, it is stuck at 0. So, normal fault case it is 0, normal case is unknown. So, all other things we have marked as X. So, just this one you can very easily see. So, all these things are X. So, only how we have written the circuit is that instead of this gate number 2 and gate number 1, so instead that this is connected to the output of a flip flop, we eliminate the flip flop and we say that F2 output. Similarly, for gate 1, it is dependent on the F1 output. So, we have said that the flip flop is not there, it is directly connected this way. So, now you see what do you require? So, we require to test the circuit. So, what we require? You can go to this last level of the circuit, this is 2 and a 1. So, we require a D over here. So, D has to be propagated over here. So, you require a 0 over here, just D algorithm. Okay. So, 0 means you require a 1 over here, you require a 1 over here, you require a 1 over here, you require a 1 over here. Similarly, so this is stuck at 0. So, you apply a 1 over here. So, you require a 1 over here and you require a 1 over here. So, this is what we are requiring over this. Now, this will actually test your circuit. So, this is the last time frame. So, we mark it. Now, to get a 1 over here. So, this is in the third or 0th time step. So, this gate is connected to the output of second flip flop. Okay. So, to get this 1 in the output of flip flop 2, so one primary input can be set at the 0th time step, that is done. But the other input 1 has to be come from the output of flip flop number 2. So, you have to write a output of the 1 from this as the previous node. Similarly, for this gate number 1, you require a 1 over here and you require a 1 over here. So, this is the primary input can be controlled, but the other input, that is C equal to 1, that is another gate, that is actually also you can know that it is the output of the flip flop number 1. So, you have to also know that the flip flop number 1 has to be a 1 to make this a 1 at time step 0. That is, in other words, we say that when you see F, that is the output F flip flop 1, that output has to be a 1 in the previous step to get a 1 in the next step. So, you write that flip flop 1 is to be a 1 over here, flip flop 2 is to be a 1 over here, but that is at the time step 0 and the requirement. And when you can achieve it, this flip flop 2 1 can be achieved at time step minus 1, and this also has to be achieved at the previous time step. So, now in the previous time step, if you want to apply F equal to 1, so what you have to do? You have to make C equal to 1 and apply a clock pulse, because the input of the flip flop 1 is directly dependent on C. So, this can be done very easily by applying C equal to 1 in the previous time step. Now, but you require flip flop output 2, output flip flop number 2 to also to be 1. But how do you achieve this? That is somewhat not very simple, because again the output of flip flop 2 is driven by gate number 1, which one of the input is primary input. So, you can directly set it at time step minus 1, but another input of this AND gate which is driving flip flop number 2 is dependent on the output of flip flop number 1. So, that has to be controlled in another time step which is one ahead before. So, to get a 1 at this, which will actually make this flip flop 1 at the third time step. So, what you have to do? You have to get a B equal to 1 in the second step, that is fine, but again another input that is actually the of this AND gate number 1 is connected to the flip flop number 1. So, it has to be controlled at the time step number minus 2. So, in minus 2, if you make set A equal to 1, so what will happen? That flip flop output 1 will be 1 in the 1 minus 10. That is what actually we are doing. So, indirectly what we are requiring, just very quickly look at the snapshots what has been done. We require a 1 over here, which is the flip flop number 1. So, to get a 1 over here, we require this AND gate to be a 1 by the primary input 1, fine. But another input of the AND gate is actually output of the flip flop number 1. So, we also have to be a 1 over here. So, how do we get it? So, this as this F1 is actually a flip flop which is controlling gate 1. So, it has to be controlled in the previous step. So, in step minus 1, time step minus 1, we apply C equal to 1 and we get it. In time step 2, again the AND gate is there. So, we require a 1 over here, another one is by this primary input A equal to 1. So, this you can very easily get in the time step 0 or the third step. on the third step. But another, this input has to be 1, it is the output of flip flop number 2. So, this has to be achieved at the previous timestamp, this timestamp minus 1. So, to get a 1 over here, you require a 1 over here. So, this can be done in the second step or timestamp minus 1 on the second stage. But again this AND gate is dependent on flip flop number 1, which also cannot be done at the current instant. So, you have to go one more stage before and you have to make C equal to 1. So, if you make C equal to 1 in this timestamp minus 2 and then you make B equal to 1 at timestamp minus 1, then what you are going to get is that you are going to get a output of 1 in the second stage, which can be directly applied to the third stage. And if you are making C equal to 1 in this timestamp minus 1 or the time or step number 2, then what you are going to get in the third stage, you are going to get a 1 over here. So, indirectly what we have already seen in the long example before, we are just writing it in a formal way. That is just some requirements. The requirements are 1 over here, a 1 over, a 1 over here. These are the two requirements are the time stage numbers, timestamp 0 or step 3. This step 3 you require this. So, this requirement, this can be achieved by making B equal to 1 and another input has to be a 1. So, which we can achieve by making C equal to 1 in time step 2 you can say, or time frame minus 1. This requirement of 1, that is again these are actually virtual primary outputs, virtual primary inputs which are controlling. So, now again this 1 is required. So, to get this as a 1, we require this one is a 1. So, which we can easily get it time frame 2 or step 3 you can say. But another input to get this as a 1 we require at this stage, we go to this stage to make this a 1. To make this as a 1, we require B equal to 1 in time frame minus 1 and also another input is there which is now dependent on the time frame minus 2, that is actually because this gate is dependent on one flip flop level 2 and one flip flop level 1. So, you have to again go back to time frame minus 2 and you have to set C equal to 1. If you do that, then this one will also become a 1 in the second stage, we will get a 1 and finally you are going to get your requirement. So, this is nothing but whatever we have discussed is nothing but these 3 stages, this stage 1, where you are making C equal to 1 and applying a clock pulse, that is the stage 1, this one. Then next is making 1 here, applying here, and the third stage is nothing but applying this one and testing this one. These are the 3 stages which we have done, we are just representing pictorially in this way. So, this is a very formal way of describing your time frame expansion method and you can solve your this thing. Okay, so, that about time frame expansion method based testing. So, in this case you have to observe that to test a single stacked fault, what you have to do in case of ATPG for combinational circuit, only one step would have solved your problem. But in case of sequential circuit, we require much more number of stages and number of stages are equivalent to nothing but your number of sequential depth of the flip flop. So, that is why you can say that sequential ATPG is combinational ATPG star sequential depth. So, that is why it is a very complex procedure and you have to also remember that any stage you may have backtracks leading into a big problem. So, in the next lecture you are going to see how we can make this very complex problem a simple one. But before that, let us very quickly see a question. So, this is a cyclic circuit and we have not considered any cyclic circuit. So, now if I ask you that can you test any fault in this circuit. So, the question is can ATPG and testing be performed for any fault in the XOR gate below? The answer is no. Why? Just we will see. Say for example, we know that the output is always a x before the circuit is starting. So, you will get a x over here. So, now if you have the primary input as 1, so your answer will be x prime, because we know that in case of an XOR gate, if the input is 1, the other is inverter. And now if your primary input is 0, you are going to get an x. Okay, and again this x or x prime will be fed back and this will be loop. So, at no point of time you can be able to get a value of 0 and a 1 over here. If you get the primary input 1, it will be x prime, if you get a 0, it will be some other thing. So, at no point of time you can get any control decision or control value to get a decision over here, because the input is dependent, because this input is dependent on its own output. So, therefore, as we cannot set the flip flop, so if you have a circuit something like this, no point of time you can convert this x to any other stuff and fault cannot be tested. So, with this we come to the closing of this lecture, and in next lecture we will see how we can solve the problem of such a huge number of test patterns required for our sequential circuit testing. So, we have to somehow reduce the number of test patterns required or the number of sequences required for testing a fault in a sequential circuit. Thank you.